Next is question number 4 from RACE-3 of the Secureum Bootcamp. We can see that this is again about our in-Secureum NFT contract, and it says that it is not susceptible to reentrancy given the absence of external contract calls. So because there are no external calls in this contract, a reentrancy attack cannot be exploited. We already know this to be incorrect because we've seen in previous questions that the on ERC-721 received callback function is called on the receiver of the NFT. So that is one place where the receiver of the NFT can take over the execution flow and re-enter the contract. But we have another one which we haven't talked about yet, which is here, which basically transfers the change, because it is possible and allowed for more ether than necessary to be passed to the mint function. This contract will not keep the amount that you send too much. Instead, it will return it to the caller, and to return it to the caller, it uses the dot transfer function, which will make also an external call and therefore trigger the fallback function of the receiver if the receiver is if the message sender is a smart contract. So we have at least 2 places already where a reentrancy could be enabled. So A can definitely not be true. Then we have B. It is not susceptible to integer, overflow, or wrapping given the compiler version used and the absence of unchecked blocks. So what compiler version are we using? We are using Solidity 0.8, which indeed has native protection against overflows. And are we using unchecked blocks anywhere? There are no unchecked blocks in this entire code, and therefore this option is indeed true. It is not susceptible to integer overflows or wrapping because the compiler version used prevents this from happening, and this protection from this compiler version is not bypassed using any unchecked blocks. It should be mentioned, however, that by introducing overflow protection, you protect against overflows using reverts. So if it would overflow, you revert instead, and reverts can cause denial of service, because if the state of the contract can be put into a configuration where it would always revert because it would always overflow, then it would deny servicing anyone who's calling it. So just because it has protection doesn't mean it is actually safe, but in this case, indeed, it cannot overflow or wrap. Then we have option C, which says it's susceptible to reentrancy during minting. We've already seen that during minting we have 2 external calls, one to return the change money, and 2 to let the caller know, which calls the callback to the caller. So can this actually be exploited? And in this case, yes, it can be exploited, because when it checks whether enough ether was sent to mint a token, it doesn't check the message.value. So it doesn't check how much ether has been sent with the call. Instead, it checks the current balance of the contract. So basically, only the first mint call could send the necessary amount. This necessary amount is now here, and it passes this check that checks whether sufficient funds have been sent to buy. And then either because we sent too much, we would be able to re-enter here, but we would only be able to do that once, because then we receive the change basically. Or, well, we could just keep every time we re-enter, we could just send back the change basically to make it send it back to us. Or instead, we could make use of the callback function if we implement that, because the entire balance of this contract is only sent to the beneficiary after after the callback has been executed. So we can re-enter the minting function multiple times and reuse the same balance before it is finally forwarded onto the beneficiary, before the amount of ether on this contract is actually reduced to 0. We can use it multiple times, and therefore indeed see this contract is susceptible to reentrancy during minting. Well, that is certainly not perfectly safe for production, and that means that for question 4, B and C are correct.